Let's solve question 3 in this video. So if the employees decide to work as a team, then they're going to choose an effort equal to this amount. Now, what's the idea here? Because they work as a team, we have to keep in mind that their utility now depends on a slightly different salary, because the salary is the base salary. Over here it's given to us in the previous video. The base salary plus half of the bonus. So we have to keep that in mind when we write our utility function. And let's just crop this utility function below, and we'll have to rewrite it a bit. So I'm gonna copy this and paste it below over here. Yes, so I'll keep that in mind when we solve the new utility function. So we'll have the utility of one individual, so utility of one individual, which is equal to the salary, the wage, which is A plus 1/2 times the bonus of the output, times the bonus of the production, so times the quantity, plus gamma multiplied with the wage of the other individual, and the wage of the other individual is also the base plus 1/2 times the bonus times the quantity, and then minus the cost of effort, minus 1/2 theta e to the power of 2. Now, what do we know about the quantity? We know something about the quantity under team production. We found it out that the quantity under the team production is the following. It's K times V times the efforts. So let's write that down, because we want to know the utility in terms of the effort. We're looking for the optimal effort, so we have to write the function in terms of effort. We'll have the utility of an individual, which is equal to A plus 1/2 times B times the quantity is equal to K times V times the effort of individual I plus E of the plus the effort of the other guy. Yes, that's the quantity. Then plus, here we have gamma multiplied with A plus 1/2 times B times the quantity, which is again K multiplied times V multiplied with the efforts of the two guys, like that. Close the brackets. And now we're here, minus the cost of effort. So let me just zoom out to get some more space here so that we can have everything in one place. Minus 1/2 theta times e to the power of 2. Now we have a utility of individual I based on his effort, because we have the effort in this term, we have the effort here, and we have the effort over here as well. And we can see that again we have this quadratic function with a negative coefficient. In other words, we will have a parabola when we're looking for the maximum point. So we want to differentiate the utility with respect to the effort, and that derivative must equal to 0. So how we're going to differentiate this? We're going to differentiate by taking the derivative of every term. So this one, derivative is just 0. Now this term, 1/2b times all of that, derivative with respect to the effort. So we'll have to keep the constants only, and the constants here are going to be the following: 1/2b times k times v, because when we open the brackets, this is the constant term next to the effort. So when we differentiate, that's what we're left with: 1/2 times b times k times v. Now this one is e of the other guy, so we're differentiating with the effort of individual I. We're not interested in that, so the derivative of the other term is just going to be 0. Now we go to the next term. What do we have here? We also have a term depending on the effort of individual I. When we take the derivative, again we'll keep the constants. Now what are the constants going to be? Well, gamma is going to be multiplied with that term, so gamma will be a constant, and then these terms over here are also going to be the constants next to this variable. So we'll have gamma multiplied with 1/2 multiplied with b, with k, and with v. And then here we'll have effort of the other guy. When we differentiate, that becomes 0, minus the derivative of the cost of effort, which is going to be again the constants: 1/2 theta multiplied with the derivative of e to the power of 2, which is 2 times e, equals to 0. Okay, so we solved all of that, and now we have our effort over here. So let's take this term to the other side. Let's take this term to the other side, because we want to have a function of the effort only. What do we have here? We have a common factor. We can see that we have 1/2 b times k times v, and over here we also have 1/2 b times k times v. So in other words, let's take this as a common factor, and we will have 1/2 b times k times v. And what do we have left in brackets? Well, here we're left with just 1, and from this term we're left with gamma, so 1 plus gamma, and that's going to be equal to this term when we take it to the other side, which is 1/2 theta multiplied with 2 multiplied with the effort. Okay, now what can we cancel out here? We can cancel out some terms. We can cancel out 1 over 2 with 1 over 2, and we can take 2 theta on the other side. So we'll divide both sides by 2 theta, such that we find out the effort of the individual. So the optimal effort is going to be equal to B times K times V times 1 plus gamma divided by 2 theta, and that will be it. And let's have a look at the answer key if that's the case. The answer key tells us 1 over 2 times 1 plus gamma times BKV times 1 over theta, which is pretty much the same as we just did over here. So the answer is true, and we are done.